So in this video I am going to look at section 2.1 here in the AS Marine Science book, where we look at tectonic processes. This might seem a bit weird when we talk about marine science, but the process of how the earth moves and how land and seabed is created is extremely important to understanding how our oceans are connected. I will be trying here to go over section 2.11, structure of the earth, 2.12, where I describe and apply the theory of plate tectonics and the evidence supporting it. I'll go over the evidence you usually ask for in marine science exam. I'll try to identify and describe the three different types of plate boundaries: convergent, divergent, and transform. And I'll explain how plate tectonics produce ocean trenches, mid-ocean ridges, hydrothermal vents, abyssal plains, volcanoes and earthquakes, and tsunamis. And that will be the main section for this video. The rest about hydrothermal events will come later. Now, on the structure of our planet, it has been known that there are hot magma inside our planet ever since volcanoes started happening in human history. But our understanding on how our planet is structured is very much an indirect science. We can't go into the center of the earth and see what's there. So everything we do is done indirect by looking at patterns of waves from earthquake, from seismic explosions, from something as bad as nuclear tests. We thereby, by seeing how waves travel through our planet, we get an idea on how our planet is built. And what's important to know here in marine science is we have an inner core, which is a solid metal. We have an outer core, which is a liquid metal, and which is a huge impact on our magnetic field, how that moves in waves. Then we have our mantle, and outside we have our lithosphere, where we have the crust, and that is where we live. So in 1912, a German scientist, Alfred Wegener, he came up with a theory that the continent on the earth was actually not standing still, they were in fact moving. Now this was at the time pretty groundbreaking, no pun intended, but the idea was that Alfred, he looked at some of the evidence, and what he saw was that rock layers on different continents, if you look at Scotland for example and North America, some of those layers look very similar. If you look at the shape of the coastlines, South America, Africa, there are also some similarities that kind of suggest that they could have fit together like a jigsaw puzzle. But also more importantly, if you look at the fossil evidence, where different animals and plants used to live and where they live now, there are some connections that would make them a lot more sense if these different continents at a time were together, and then as they split apart, evolution would evolve differently on each continent, but they would have been together at a time, because if they've been separated at all times, some species probably couldn't have moved from one place to another. Now, at the time, this theory was not widely accepted, but with modern science, we get later on to a part where we now know that this theory is probably how things are. Now, as we move up in time into the 60s, this theory of plate tectonics kind of become more and more mainstream, and it does so because now we have a theory explaining why it happens, and we also have more and more evidence. The why it happens is that, as you remember, the inside of the earth is liquid, not the central core, but the rest is liquid hot metal on molten rock, and our model is that the plates kind of drift on these sea of molten metal and rock. Now these are huge continents here, the plates are huge things, and they move slowly, but they do move. And we can see that not only from the original things that Alfred suggested, which is the geology of mountains, fossil evidence, and the shape of the coastlines, but we can also see it from two new things we discovered here, which is paleomagnetic stripes and seafloor spreading. And these are the two things we're now going to go into more detail with. But the accepted theory is now that we have these plates which are, although slowly, drifting on this kind of very dense ocean below it. So the two new pieces of the puzzle, seafloor spreading and paleomagnetism, came along in the 40s and the 50s, and it's one of the few good things that came out of World War II. During World War II, there was a lot of mapping on the seafloor, as is important when you're hunting, fighting submarines. And during that, it was discovered we have this huge mountain chain all the way down the Atlantic, the mid-ocean ridge. And you can see that the seafloor there is continuously being created as we have a divergent boundary. So hot magma comes up. And we can see that the newest seafloor is close to it, and then moving away we get older and older and older seafloor. And for this to happen, well, the plates need to continue to move apart. So we get a continuous creation of seafloor here, which is something we call seafloor spreading. The other piece of the evidence is what we call paleomagnetism. When again we have seafloor spreading, we have hot magma coming up, and when we have hot magma, it's of course liquid, which means whatever part of iron or the metals that are in there is moving freely. When then the magma cools down, those pieces of metal will then lock in place, and they will tend to lock in place depending on the magnetic field of our planet. It has long been known that we can measure the magnetism of these rocks, and when we do so, we see that the magnetic direction in these rocks change place. So we have north here, and then we have north here. And we know that Earth, North and South Pole, they change place every around 200,000 years. So the fact that we see the same pattern in rocks means the seafloor is continuously being created, and we can see how old it is further away from the ridge, or how new it is. So these two pieces of evidence clearly support that we have an active Earth and that we have tectonic plates that move. Now, in our current theory of plate tectonics, plate tectonic movement happens because we have these convection currents due to temperature difference in our hot center of the Earth. So we have these currents of hot magma, melted rock rising up, cooling down, moving in these circles, just the same as we see when we see cloud creation, water vapor going up and so. But this is so dense and so big that it's slowly pushing, which means that our different plates are only moving a few centimeters a year, but over a long time. That's enough to make the planet we live on. And just shortly, we then have three different kind of boundaries. We have convergent boundaries, which is where the two plates are pushing together. So two plates are meeting, and we'll talk about later on what that can do. Then you have divergent boundaries, which is when the two plates move apart, as we see on the mid-ocean ridge in the Atlantic. And then last but not least, we have transform boundaries, where our two plates are moving sideways to each other. What these different kind of boundaries can do to a seafloor will be our next point. So with convergent boundaries, we have the two plates pushing together. When that happens, the densest of the plates will go into the subduction zone, where it kind of moves down, can push down, and the other will push into it and maybe start rising up. That is why this push we see down here is what gives rise to the trenches in the ocean. So that's why we see most of the trenches we see in the Pacific, where we have the plates pushing together. It can also give rise to mountain ranges, as one go down and the other one gets pushed up. We see plenty of the mountain ranges on land getting created from this. Also often when we do that, we'll secondary see volcanoes pop up from the activity below, get up to the cracks. So we'll see a lot of volcanic activity around the convergent boundaries. On divergent boundaries, we have the plates moving apart. Well, this is where the hot magma will tend to come up, as it do all along the mid-Atlantic Ocean ridge. And as the hot magma then leaks into the water, it will become solid and start forming underwater mountains, or, in the case of a place like Iceland, islands above the surface. This also means this is where we have a lot of new rock being created, and we have new seabed being created here at the center, while as you move further away, the sea bottom gets older. Last but not least, we have the transform boundaries, which is where two boundaries slide like parallel to each other. When that happens, we have no creation of new rock, we have no subduction zone, but what we do have is usually a high amount of activity of earthquake, as we have this huge power here that will then crack, and these earthquakes can lead to tsunamis or earthquakes on land.